Understanding light passing through a diffraction grating screen. A single light, in this case red, is projected on a screen after passing through a diffraction grating. On the back screen, the red light is spread out into a geometric pattern. How does a diffraction grating screen work? Diffraction grating screens have many vertical lines or slits invisible to the human eye. In the market is sold by the number of lines per millimeter. This short video shows the white light from the ceiling separated into its color components. When the white light passes through this screen that has many narrow slits, it diffracts. After diffraction, the light wave recombine with each other by constructive and destructive interference, producing specific wavelengths which correspond to a light color. For example, the red one is longer than the blue one. On this screen, the range of wavelengths is showing in nanometer from 300 to 700, and the corresponding color range for each wavelength. In contrast with white light, which is composed by many colors, a laser with a single red color has a specific wavelength. When it passes through a diffraction grating, will diffract and recombine as well, but will produce the same original color, which is red. But the question is, why is this pattern formed? In the following slides, I will cover the basic explanation for this result, the formula involved, and solve two practice problems. So what is the information we need from a diffraction grating screen? We need the distance between lines or slit separation. How we do determine the value of D? So in this case, it's 500 lines per millimeter. So D is the inverse of this, N, which is number of lines per millimeter. So when we flip the units and solve for 1 over 500, we have 2 times 10 to the minus 6 meter per line. So now I'm going to explain the geometric pattern formed on the screen. So an incident light with a wavelength passes through a diffraction grating which contains many slits, gaps between lines. After passing through a diffraction grating, this light is projected on a screen, and the dotted spot at the center on the screen is called the zero order. Then a sequence of dotted lines evenly spread out will show above and below the zero order. The dotted spots above and below the zero order are numbered first, second, third, and so on order, and each order corresponds to a bright spot. Now, to understand the angle that any order makes with the zero order or with the horizontal one, we need to look all those lights as a ray like this, and the angle that makes is from the zero order to the specific order that the problem is talking about to involve. So we have angles above and below the zero order. So the bright spots are very sharp. They're also called maxima. And between the bright spots, we have an area called minima. So the formula to solve diffraction grating problems is this one, where D is the distance between slits or the line separation meter. The angle is the angle the horizontal line makes with any order. N is the number of order of the diffraction, and lambda is the wavelength of the light source. Practice problem 1. A red light of wavelength of 700 nanometer diffracts through a diffraction grating of 300 lines per millimeter. which means each millimeter we have 300 lines. Calculate the angle, the second order maxima. So here is our zero order, and our second order is right here and is looking for this angle. We are using this formula, and this is the data table. So lambda is the wavelength of the light source, which is 700 nanometer. The number of lines is 300 lines per millimeter. The grating separation is the inverse of this data. Is looking for the angle of the second order, and n is the number of order, which is 2. So first we need to calculate the distance between the slits. So we know that the relationship between the distance and the number of lines per millimeter. So we do our substitution, we flip the units, and now we need to convert this to meter. So milli is 10 to the minus 3. And that's what we have in scientific notation is 3.3 times 10 to negative 6 meter per line. So now we can do our substitution to find this angle. So D is 3.3 times 10 to the negative 6 times the sine equal to n is 2, and the wavelength in meter, we have to convert nano 10 to the minus 9. Okay, so now we isolate sine of the angle of second order, and we find the value, and we calculate the inverse of a sine of this, and the angle is 25 degrees. Practice problem 2. A monochromatic light of wavelength 5.3 times 10 to negative 7 is incident normally to a diffraction grating. So the first order is observed in an angle of 15.4 degrees. So the first order is the angle that it makes with the zero order or the horizontal line. And now is asking to find the angle between the second order. So this angle right here, right? The angle from this to the zero order, and find the difference between both angles. So we are going to use this formula, and that's all the information that we have. The wavelength, the first angle is looking for the difference in angle. We don't know D. We don't have how to calculate D in terms of the numbers of lines per millimeter because didn't give you this information. We need to use this formula to calculate D, and the number of order, we are dealing with first and second order here. So let's solve this problem by steps. Step 1, let's use the diffraction grating formula to calculate D, which is the separation between lines. So we are going to use all the information for the first order. The angle is 15.4, n is 1, and the wavelength is this value here. So then we calculate D, and D is 2 times 10 to the negative 6 meter. Now on step 2, we are going to use the same formula, and now to all information relate to the second order. So now n is 2, the wavelength is the same value because, like I explained previously, that light is going to produce the same color of light. So here we have this wavelength, and this D is the same because that's information from the diffraction grating. So we didn't change the diffraction grating. Now the angle is 32 degrees. So the last step is to calculate the difference between both angles. So now we have the second order angle and the first order angle. So now the difference is 16.7 degrees. So that's the final answer.